In this video, I'll show how to use a couple of Pytecplot scripts to analyze bubbles in a fluidized bed simulation in Barracuda. For this example, I am using a version of the Kuiper's training problem that has been modified a little bit to produce more bubbles so that we can get a little bit more interesting information out of these scripts. So I'll go ahead and click View Results. And if we look here, what I've done is I've taken our traditional Kuiper's training example, put more of a uniform flow BC at the bottom so that more small bubbles are created, and we'll see those small bubbles grow as they get higher in the bed and they're coalescing together. Just for a quick visualization of this, if we load all of the solution times here, what I did is I ran this problem from 0 seconds to 5 seconds. I output a Tecplot file at every 0.2 seconds, so not super high resolution, but if we play through this, we can kind of see that, by 2.5 or 3 seconds, there are bubbles throughout the bed. And what we'll do to illustrate this script is we'll look at just the data from 4 seconds to 5 seconds. So here, let's go ahead and do load Barracuda data and say that we only want the last 5 of these files. So actually this will start from 4.2 seconds and get up to 5 seconds. So let's refresh, reload, and I'm going to go and move this a little bit. So now if we go back here, we'll see our first loaded solution time is 4.2, and we have 5 files just for illustrating how the Pytecplot script works. As was shown in the webinars that are related to this script, you will need to create some blanking constraints here. So let's go to plot, blanking, value blanking. In this case, I'm going to change this to a cells view because this will make it a little bit easier to see what's happening. So if we color cells by particle volume fraction, what we want to do is isolate these cells that have relatively low particle volume fraction because these are our bubbles that we care about. And so we'll say, all right, we're going to blank on particle volume fraction, and we want to blank anything where the volume fraction is greater than some threshold, right? And so let's choose like 0.25 as an example. So if we do that, now we see that we can isolate these individual bubbles. It might take a little bit of exploration on this. I would say somewhere between 0.25 and 0.35 might be reasonable limits for isolating bubbles. The other thing here is in this example there's a large freeboard space and we don't want to be analyzing that. So let's add a second constraint where we're blanking if z is greater than or equal to 0.5 meters because our bed goes up to about 0.5. And so, okay, now we can see we've isolated these bubbles that are just in the fluidized bed portion of the system. Okay, and let's go ahead and save a layout file because the script does require a layout file to work. And here I'm just going to give it the same name as one that I was testing with earlier, bubbles last 5 solution times. Generally, I like to use this relative paths option just so that this layout file could be moved to other directories and not remember the original directory that it was in. So let's save that, and yes, we want to overwrite it. And now we're at the point where we are ready to run the Pytecplot script, and so I'm going to do scripting Pytecplot connection, accept connections here, and then we'll go back to our Barracuda GUI, and we will open a terminal in this GUI, and Python is already installed and configured on my machine, so I see the base indicator that says that Anaconda Python is in its base environment, so we should be ready to use it here. And we'll go ahead and issue the command that we want to use for running this script. So the way that I would recommend running it is Python -O for optimized, and then we'll give it our script name, which in this case is today's date, bubble extraction and analysis.py. We want to run this in connected mode, so we'll use the -- connected option. We need to specify our layout file that we just saved that defines the blanking criteria. And then we need to specify a file name for writing out the extracted bubbles that the script is going to create. So we'll go ahead and just call it fluidizedbedbubbles.plt. That's where the data is going to go that this script will create. Okay, so if we hit enter, we'll see that the script starts running, and it'll tell you which solution time it is currently working on. And so this is based on information from the layout file. And so our layout file knows that we want to load 4.2, 4.4, 4.6, etc. And so it'll show you where it is. And as it's running, what the script is doing is it's creating new zones in the Tecplot data set. And it's also writing out some data to several text files that we can use for plotting bubble statistics. So if I look in my directory, the two files that it's creating, one is bubble count versus time. And so if we open that, we'll see that the header information is here, but the data is not here yet because the script is running and it's doing the data analysis. The other file is called bubble information comprehensive. And if we open this, you'll see, if we just kind of compare these two headers, this file tells us how many bubbles we have versus time, so it's just 2 columns. This file is a lot more columns, but it gives us information about every single bubble in the system. So, and once this gets past one time step, oh, there it is. If we reload these files, we'll see what this information looks like. Especially for the comprehensive one, we'll see in this case, at this solution time, 4.2 seconds, it looks like we have 32 isolated bubbles in the fluidized bed. And then this script records information about what is the X, Y, Z center position of each bubble, what is the volume of each bubble, what is the diameter of each bubble. And in this case, the script by default is set up to assume that bubbles are kind of 2D pancakes, but that's only because of this example problem, right? This is kind of a 2D example. So if you want to do 3D bubble diameter, I'll show you how to do that in a second. The script is also calculating the bubble rise velocity and the average U, V, and W fluid velocity inside of each bubble. So you're going to get a lot of information from the script about every bubble in the system, and then I'll show you there's a plotting script that takes this information and can create some plots for us that are useful. So here, let's take a look at this script. I do want to point out this idea of the bubble diameter, because this is something you may need to change if you're looking at a 3-dimensional simulation. Here, let me find it. So here's the Python script. So if you have a 3-dimensional simulation, go ahead and edit this script and find this section here that talks about the bubble diameter. And you'll see here we're assuming a thickness that's equal to our domain thickness for this kind of pseudo 2D bed. But if you have a 3-dimensional bed, instead of calculating the radius with this line, you should replace this calculation with this, which would assume a spherical bubble rather than a thin cylindrical bubble. So just be aware of that. That could be important depending on what your system looks like. The rest of the script should be okay. It's pretty generic in terms of like just collecting data, writing it out to some text files, creating zones, things like that. But that aspect of the script could need to be adjusted. If we click back in here, we could probably reload some more data. We could see how far it is. So it looks like we've gotten to 4.4 seconds. Okay, maybe 4.6 now. Okay, so we've analyzed a few files. We've got a couple more left. And as you can see, this could take a while. This is a relatively small simulation, but it still takes a bit of time to go through, extract the zones for the bubbles, do the calculations for each bubble, and so forth. So just make sure that you give yourself enough time. And I would say maybe don't try to do this analysis for hundreds of files, right? You may want to limit yourself to analyzing 10 or 20 files to get some representative information about the bubble sizes and bubble characteristics in your system. Or if you do need it to run much, much faster, if you purchase a full license of Tecplot, then you can run in batch mode rather than connected mode. And batch mode can run a lot faster. And you can also run in parallel to use multiple cores at the same time. And so for maximum performance, a full Tecplot license is helpful. compared to Tecplot for Barracuda, which is limited to running in connected mode. So just be aware of that. If that becomes a real limitation for you, then contact the Tecplot team to talk about buying a full license. Okay, so this is almost complete. Let's take a look at our files one more time. Okay, we're down to 4.8 seconds. And we can see here these are fairly consistent, right? We have about 30-ish bubbles as time goes on, from like 4 seconds to 5 seconds. It's not changing a whole lot, but there is some variation. And oh yeah, let me show you this plotting script as well. So once this comes up, we will illustrate how to plot some information from the data that's been collected, right? We can do histograms of bubble size, either over all time or over some specific time. We can do number of bubbles versus time, bubble size versus elevation, bubble rise velocity versus size. There's a lot of different information that is possible to extract. Okay, so it looks like we're done. All of this is out to 5 seconds. If we look at our terminal, it'll tell us how long did that take to run in terms of how many minutes, or actually this is seconds, 365 seconds. And so that is complete. So now let's do the plotting script real quick just to illustrate how that works. And this one has today's date and plot bubble properties. So if we do that, as I mentioned, histogram over all time, so we can see that this is just the number of bubbles that are in a certain size range. And so we have a higher number of small bubbles, and then they coalesce into a smaller number of large bubbles over this period of time that we've analyzed. You can also limit the time to a minimum and a maximum time, and in the script you'll see the syntax for doing that, right? Python has some nice syntax for applying filters like that. So we can see that you can do that sort of analysis. We can plot the bubble count versus time just to see how steady it is. We can do more of a scatter plot. We would expect that bubbles start small at the bottom and get bigger as we go to the top, and that's what we're seeing in this data, is that as you increase elevation, your bubble diameter also increases. And kind of inversely, we would expect small bubbles to have the highest rise velocity and large bubbles to have the lowest rise velocity. So with this sort of data, you can kind of quantify that and see what that trend looks like. So this script will put those plots up on screen. It will also save those plots to PNG files. So just be aware of that. We're illustrating how to do that through that Python script. Okay, so then the other thing that is probably of interest to a lot of people is just visualizing some of this data. So as the script was running, it created multiple zones of these bubbles with the volume information and the diameter information and rise velocity and those sorts of things. So you may want to make an animation showing those things. So here you can go back to your Tecplot window. What we'll do here is we'll turn off the cells zone, and this extracted cells zone, this is what the script created. So let's go to surfaces. We will say we want to show boundary cell faces. And now if you adjust your contour details, what you'll see is you have some new variables here, right? So bubble number, bubble XYZ position, volume, diameter, rise velocity. So just to illustrate, let's look at bubble diameter. So we can see that we can color the bubbles by that parameter. If we want to show our vessel, sometimes in this case it might be easier to show the STL file. So let's do that. Let's say show the STL zone. Let's show the shade of that zone and show the shade layer. And then let's do tell that zone not to use blanking. And actually let's tell the extracted cells not to use translucency. And then here we can say, all right, we want you to be a little bit more transparent just so we can see the vessel, but we can also see through it. So this sort of visualization could be useful to just make an animation or make some still images about what does my bubble diameter look like. And of course, if we copy and paste this frame, you can do frame tiling to get several views of bubble information side by side. We can link those frames in terms of solution time and 3D plot view, so that way they're kind of tied together spatially and in time, and then we can change this one to something like bubble rise velocity so that we can see how these parameters change together, right? And you can export animations from these sorts of views. So hopefully that gives you a good idea of how to use these scripts. It should give you some really nice information about bubble properties within fluidized beds, and hopefully it's helpful for your analysis. So that concludes this video.